Transformation of phases. Behavior of gases at high pressure. 1. At high temperature, the value of Vv increases with increase in P. Second, at low temperature, the value of Pv decreases initially with increase in P. It becomes a minimum at a particular pressure and then increases with increase in pressure. 3. At temperature below the critical temperature, there is a sudden decrease in the value of Pv with increase in pressure. This corresponds to the change of state from gas to liquid. When the liquefaction is complete, Pv gradually increases with increase in P. The ideal gas equation is only applicable to the ideal gas for low pressure and high temperature, but for real gas at a high pressure and low temperature, we cannot use ideal gas equation. Hence, we use van der Waals gas equation. This equation is nothing but the modification of gas equation. 1. Correction for pressure. We know that at a high temperature and low pressure, the intermolecular distance is very large and hence cohesive force is negligible. But for real gas, the cohesive force is of greater extent, hence it needs some correction. The correction for pressure depends upon A. The number of molecules striking unit area of the walls of the container per second, and 2. The number of molecules present in a given volume. Both the factors also depends upon density. Hence, correction for pressure P proportional to P rho square proportional to 1 by V square. This implies P equals to A by V square, where A is a proportionality constant. Hence, correct pressure equals to under bracket P plus 1 by V square. Now, correction for volume. The correct volume equals to V minus B, where V equals to 4 into actual volume of the molecules. Critical constant. The critical temperature and corresponding values of pressure and volume at the critical point are called the critical constant. At the critical point, the rate of change of pressure with volume dP by dV equals to 0. This point is called the point of inflection. According to van der Waals equation, under bracket P plus A by V square, bracket close, into under bracket V minus B equals to RT for 1 mole, and P equals to R into T by V minus B plus A by V square. Differentiating with respect to V, we have dP by dV equals to minus R into T by under bracket V minus B का whole square plus 2A by VQ. Equation 1. At critical point, dP by dV equals to 0. In this case, T equals to Tc and V equals to Vc. Hence, minus of R into Tc by whole square of under bracket Vc minus B plus 2 into A by Vc square equals to 0. This implies 2A by Vcq equals to RTc by Vc minus B to the power 2. Again, differentiating equation 1, dP by dV equals to minus RT by V minus B का whole square plus 2A by Vq. We get d2P by dV square equals to 2 into R into T by under bracket V minus B to the whole Q minus of 6 into A by V to the power 4. At critical point, d2P by dV square equals to 0, and the T equals to Tc and V equals to Vc. This implies 2RTc by under bracket Vc minus B to the power 3 minus 6 into A by Vc to the power 4 equals to 0. Hence, 6 into A by Vc to the power 4 equals to 2 into R into Tc by under bracket Vc minus B to the power 3. Now from equation A and B we get Vc by 3 equals to Vc minus B by 2. This implies Vc equals to 3B. Substituting this value we can get Tc, that is critical temperature, equals to 8A by 27 Br, and Pc, critical pressure, A by 27 Bs. Relation between critical parameters RTc equals to 8 by 3 PCVC. Hence 8 PCVC equals 3 RTc. Clausius-Clapeyron equation dP by dt equals to Qy T into under bracket V2 dash minus V1 dash, where Q12 is the specific latent heat observed in the transformation 1 to 2. V1 dash and V2 dash are the specific volumes of phases 1 and 2. A saturated water vapor is contained in a cylindrical vessel under a weightless piston at a temperature T equals to 100 degrees Celsius. As a result of a slow introduction of the piston, a small fraction of the vapor, delta M equals to 0.70 gram, gets condensed. What amount of work has performed over the gas? The vapor is assumed to be ideal. The volume of the liquid is to be neglected. From the equation, it is clear that the sum volume of the gas is condensed into liquid, but the volume of the liquid is negligible. Hence, work W equals to integration dW integration P dV equals to integration P into integration dV VI to VF equals to P into VF minus VI equals to PVB, because V equals to VF and VI is equal to 0. Since the vapor is to be ideal, and hence it will obey ideal gas equation, PV equals to nRT equals to delta M by M into R into T. During the condensation process, the temperature does not change. Actually, the work is done for liquefaction of gas. Hence, A equals to work done equals to delta M by M into RT. Putting delta M equals to 0.7 gram, capital M equals to 18, R equals to 8.31 joule per mole per Kelvin, and T equals to 273 plus 100, 373 Kelvin. Hence, we get A equals to 120 joule answer. Alternatively, we can solve this. We have work done by the gas equals to VI to VF P dV, or equals to P into VF minus VI. Hence, work done on the gas minus of P into under bracket VF minus VI, or equals to P into VI minus VF. Now, PVI equals to MI by M into RT, and PVF equals to MF by M into RT. Hence, A work done equals to P into under bracket VI minus VF equals to PVI minus PVF equals to under bracket MI minus MF by M into RT equals to delta M by M RT answer.